Welcome, one and all, to the Cool Worlds podcast with me, your host, Professor David Kipping. This week, I am joined by Ramesh Narayan, renowned professor in the Department of Astronomy at Harvard University, and also has been elected as a member of the National Academy of Sciences, a highly prestigious title to hold. Ramesh is trying to accomplish that which seems almost impossible. He is trying to model some of the most extreme environments in the universe, and by doing so, he is pushing the boundaries of our capabilities of modeling, combining magnetohydrodynamics, radiative transfer, and general relativity all into one self-consistent package to model some of the most difficult and hardly imaginable environments in the universe, such as supermassive black holes. In fact, he was one of the architects of the EHT, the Event Horizon Telescope image of Messier 87, a photograph that stunned the world when we first saw it just a few years ago. So please do enjoy my conversation with Ramesh, and I hope you learn a lot about these extreme places in the universe. First question I want to ask you is, what is a black hole? Where is the nearest black hole? How many black holes are there? Give us the basics about a black hole for someone who's just learning about them.
Yeah, thanks, David. It's a good place to start. So a black hole is a concept that basically came up after Einstein developed his so-called general theory of relativity. Mm-hmm. This was a theory where he combined relativity and gravity, a common theory. So among all the interesting things that came out of that theory, there was this idea of a black hole. And here the idea itself is very simple. We all know that there is gravity. Gravity pulls things together. And in normal physics, you can pull them together, but they finally will stop. Like, all the material on the Earth, it's all being pulled together by the Earth's own gravity. But the Earth, is finally happy. It's reached a stable configuration and we can live on the Earth. We get pulled in, but nothing dramatic happens. Mm-hmm. When you include general relativity, under certain conditions, this gravity becomes so strong that nothing can prevent it from pushing everything down to the center. So it is like taking the Earth or the sun or any big object, and its own gravity is so strong that it cannot resist itself. And everything gets pulled down to a point, true geometric point, according to the theory. It's what's called a singularity. So everything becomes extreme. And so it's something that, we are not familiar with from earlier physics. And so this is a black hole. It's something that's supposed to happen according to the theory. It's, in fact, almost unavoidable under many circumstances, especially when big stars die. And so this object is supposed to form. And so, in fact, it doesn't have a surface. It has instead something called an event horizon. We can get into that a little later. But these are the characteristics of a black hole. Infinite density in a point right at the center, or something similar to a point, and something called an event horizon. Now, so let me just answer the rest of your questions. So this is what theory said. And for a long time, nobody thought this is real. It's okay. It's his theory. And even Einstein himself never really believed that they are real. But a few years after he died, astronomers started finding objects, which we now believe are black holes. So there are big black holes, there are little black holes. You asked where is the nearest one? Well, the nearest one that we know of is a few hundred light years away. There are doubtless others that are even closer, which brings up the next question you asked. How many of them are there? Mm-hmm. So the most numerous kinds of black holes are those that have a mass of roughly 10 times the mass of the sun. Can be anywhere from 5 to 50, okay? It's a range. So these are what are called stellar mass. They're like stars, a little bit heavy. Of those, we think there must be about 10 million just in our own galaxy. And if you count all the galaxies in the universe, that's a huge number.
Right. Right.
That's the little guys. Then there's also a big one. In our own galaxy, there is a big black hole with a mass of several million solar masses. And there are even bigger ones in other galaxies. There's one in each galaxy which sits in the middle.
So when, looking back at the history, just to catch that, you said something really interesting there, that people didn't believe it, right? Yeah. When the equations showed it, and I guess this does happen often in science, you think of like Dirac's antimatter was, similarly, people thought, well, that's just a curiosity of the math. There isn't really this thing called antimatter, but it turned out there is. And I'm kind of interested in that historical journey. So Einstein published GR in 1915, late 1915, and soon after we had Schwarzschild publishing his metric, I think within a couple of months or so, right? It was very fast after. When did the idea of a black hole start to first be proposed, and what was the community, not just Einstein's, but the community's reaction to that?
Yeah, this history is really interesting. So like you said, Einstein released, or rather publicized, or gave a talk on his general relativity towards the end of 1915. Mm-hmm. And within weeks, Schwarzschild found a solution of Einstein's equations, something that Einstein had not found. Schwarzschild found it. This was for a spherically symmetric mass distribution. And he wrote to Einstein and said, look, I've got this neat little solution. And Einstein was flabbergasted. He said, I never thought somebody would find a solution, a real solution of my equations, because Einstein had used approximations. So anyway, Schwarzschild came up with a solution. Einstein loved it. And then for decades, people were trying to understand what that solution meant. They didn't immediately catch on that it's a black hole. They realized that something funny happens at a location that we now call the event horizon. So not at the center. The center has got infinite density. Okay, crazy things will happen there. But at this event horizon, which is at a finite radius, the equations do very strange things. It's almost as if things blow up there. And so Einstein struggled with this. Many others struggled with this. They thought the solution is not correct, cannot be used inside that radius. It was only, I think, by about the late 30s, 40s, 50s, that people finally came to grips with what this all is all about. And I think Einstein followed some of that. So at least they realized that this crazy behavior at the horizon is not real. But it still left open the question, do these things really form? Because they have such weird properties. That, I think, was settled when we started finding the objects. But there is still an open question. This infinite density at the singularity, it bothers everyone. And people are now hoping that that may be an artifact of the theory. When we fold in, see, what Einstein did was folding in relativity and gravity. He didn't fold in quantum mechanics. So now the hope is when we also fold in quantum mechanics along with gravity and relativity, and this is what string theory and other advanced theories in physics are trying to do, that will finally solve the problem of the infinite density. Maybe it'll be a finite density. We don't know the answer. So that is still an open question, but as far as we are concerned, what matters is what's outside the horizon, event horizon. That part of it, I think we are all happy with, in the sense it's real. The real objects are there. The physics is correct. Every test we have done seems to confirm that the equations are okay.
I mean, even I remember learning when we introduced to black holes even at college, how even Newtonian physics predicts almost a form of it, right? Because it's just the escape velocity is this well-known equation that we all learn when we're thinking about rockets or interstellar travel or something. And even in Newtonian physics, you can arrive at a escape velocity which equals the speed of light for a certain object. I think you end up with a factor of 2 wrong, right, for the actual size of the event horizon. But the principle of something that has an escape velocity faster or as fast as the speed of light exists even in this classical idea. Now, what I'm curious about is in that classical idea, you could imagine that object not being of infinite density, not being a singularity. It could be just a very, very dense, degenerate matter object of some kind, what is it about GR that implies it has to be infinite density? Why can't it just be something extremely dense?
Lovely question. Yeah. And you've made a number of interesting points there. So you're right. Within Newtonian physics, people recognized that if you made an object compact enough, the velocity you need to escape from the surface of that object can be greater than the speed of light. And fine, so not even light will escape. And that's, for all practical purposes, that's like a black hole. And this idea or this concept was introduced already in the late 18th century, more than 200 years ago. Mitchell and then Laplace, these are, big scientists of those days. Those objects, however, would have finite density still, okay? General relativity says if you try to make an object smaller than this event horizon radius, which is equivalent to saying so small that the escape velocity is greater than the speed of light, you cannot keep it stable. At that point, the inward pull of gravity will overcome any pressure, any resisting force that the object can possibly apply. This is such a weird statement. Ultimately, if you ask where does it come from, it's that, pressure. Pressure is what we use to resist, some push or pull. Pressure itself is a form of energy. Energy is a form of mass, according to relativity, and mass makes gravity. So you take this object, or you think of the object itself, it's a thinking thing, and it says, oh my God, the gravity is too large. I'm going to build up my pressure to stop the gravity. But that pressure makes energy, makes mass, and it makes gravity even stronger. So it becomes a kind of, it's chasing the goal all the time, and it just goes to higher and higher pressure and collapses. It's just never able to generate enough pressure to stop the corresponding gravity. So this is what came new from general relativity.
And does you said that maybe quantum mechanics might resolve this. Do you have an opinion about that? Does the singularity bother you?
No.
Do you seek a finite density solution from QM or something?
Absolutely. I mean, I'm not qualified to do that kind of work, but that singularity really bothers me. It's singularity in the sense of infinite density, but it's also a singularity. In fact, let me mention, Roger Penrose shared the Nobel Prize in 3 years ago, 2020. And he's a mathematician. He proved something called geodesic incompleteness. Okay? It's a technical term. What it means is if you have a black hole as described by general relativity, and you send something through the horizon, maybe you fall in, or a particle falls in, light ray falls in, whatever, falls in, okay. That guy has to continue on and reach the singularity or do something weird. Okay, fine. What Roger proved is, it's called geodesic incompleteness, which in my simple terms, what I would say is, this particle or you will keep going and you'll reach a point where actually time loses meaning. It's not just that you get crushed to infinite density. Okay, I don't like that, but I can imagine that something gets crushed to infinite density and then stays there at infinite density. That's not what the mathematics says. Mathematics says at the same time, even the concept of time kind of goes away or becomes multi-valued, undefined. You take your pick, but something really weird happens. That's the part that bugs me. I don't like that feature. And the hope is some additional version of the theory, and this will be the quantum mechanics version, will kind of resolve that problem. It may still be very high density, but not infinite probably. And I hope time doesn't stop. That time at least as a concept, still continues.
I feel the same way. I hope that's true. And I also hope it's not me that's the test particle.
No, absolutely, yeah. Right. But you won't feel a thing.
That's true.
And in fact, there'll be no time
Even
to feel
so.
anything. Yeah.
Now, these subjects are so fascinating. I think that, when you talk to the public about astronomy, black holes always comes up. And, people always wonder, will the sun become a black hole? It's one of the first questions my son always asks me. He's 4 years old and he's fascinated by them. And I guess it is, obviously the sun is not massive enough to become a black hole, but it is interesting to ask, what is the lowest mass black hole that we could have? And so I think it's true that if you have something that's around 2.5 solar masses and it's just a cold, inanimate object, GR should predict that thing should just collapse down. And yet, correct me if I'm wrong, but we don't know of many black holes in the range of, say, 2.5 to 5 solar masses, 5 times the mass of the sun. But we have black holes more massive than that we find. Is that telling us something? Is there's kind of this gap here, right, of a paucity of black holes in this low mass region? Is there something missing in our theory or in the formation models? Why aren't we seeing these, or are we seeing them? We're just missing them somehow in our telescopes at the moment.
All of these are possibilities, but you're right. Based on what we have observed through X-rays primarily. Electromagnetic radiation of black holes in our galaxy, it does appear that the ones that we can see are above about 6 times the mass of the sun, 5, 6, choose a number there, and it seems to go up to maybe 20, 30, or possibly even beyond. Meanwhile, another kind of object, which is not a black hole, the neutron star, that fellow goes up to about 2 or 2.5 solar masses, what we have observed, and there's a gap. That gap could be just that we are unable to see them for whatever reason, that they're there, that there's a continuous mass distribution. Below 2.5 they're neutron stars, about 2.5 they're black holes. This could be the case, but then we have to explain why we are not seeing these guys in the middle. There should be a lot of them. Partly, I think this is getting a new direction in the last few years from gravitational waves. So this is a new window that's been opened up. Using gravitational waves, people are finding black holes in binary systems. And there is some hint that some of those black holes they are finding may be sitting in this gap.
So this is from LIGO you're talking
This
about?
is from LIGO, the Gravitational Wave Observatory. I don't think they've filled up the gap. I don't even know how many they have found, maybe 1 or 2. But that is something we should look forward to, because suppose there is a reason why with electromagnetic radiation we can't see in the gap. Gravitational waves are a completely different channel. They probably are not bothered by this gap, and if they are there, they should see them. So I think we should wait to see whether there's a true gap or not. But based on the evidence so far, there is a missing piece. And then, why is it the case? Why is there a missing piece? That you have to go back to how these objects are formed. It is possible that, you can start with stars with a whole range of masses. The smaller guys, when they die, will become neutron stars. And then if a guy is slightly above the maximum level for the neutron star, something about the way it behaves changes, and you just don't have these objects in the middle. I mean, I can come up with stories, but this will go into too much detail. But basically, it is not that difficult to imagine scenarios in which a gap would naturally form. But I want to correct one other thing that you said right in the beginning about this 2.5 solar mass limit. This is a limit not coming from physics. This is a limit coming from how stars evolve, die, and finally make either a black hole or a neutron star or a white dwarf. So in that story, it's true. We are not going to make anything smaller than 2.5 solar masses. However, in principle, physics allows black holes of any mass. The Earth itself, if you had a really giant machine that could squeeze the Earth, the Earth is doesn't want to be squeezed, but let's say you squeeze it. Take the entire Earth and squeeze it down to 1 centimeter. It'll become a black hole. And it won't come back to be the Earth. That's it. It'll become a black hole.
It's irreversible.
It's irreversible once you've made the black hole. If you squeeze it down to 3 centimeters and release it, like a powerful spring. It'll just
Yeah.
come back. And of course, it'll all havoc after that.
Yeah.
But it'll become the Earth finally again. But there is a kind of a hump. You cross the hump at around a centimeter, the Earth will become a black hole. The sun can make a black hole if you squeeze it inside a kilometer, and so on. Yeah.
I think that's what makes them so captivating and terrifying at the same time.
Terrifying, yeah. And you can be made into a black hole. Just have to squeeze you really small.
Again, let's not involve me in black holes if we can help it. You did mention something interesting about this gap that this in terms of the observations. You mentioned X-rays as a way of detecting them, and so that immediately might confuse someone who's not so familiar with black holes, because the name black holes implies there's no light coming off the thing whatsoever. It's black by definition of the name. But of course, if that were true, we wouldn't know of any black holes out there in the universe until LIGO maybe. And so maybe you could talk about that. Why, counterintuitively, how is it that a black hole shines?
Yeah. Thank you. Yeah. I kind of went quickly over that.
Yeah.
Right. So these particular X-ray emitting black holes I was talking about, these are black holes that happen to be in orbit with a companion star. So these are two objects going around each other. One guy is the black hole. The other is a normal star, maybe like the sun.
Mm-hmm.
Now, in addition, these are binary systems which are quite close together. The two stars are close enough that the black hole's gravity has a strong effect on the star, and it's pulling gas from the star and eating it, basically. Mm-hmm. Its gravity is so strong. Even though the star is in orbit, surface material keeps getting pulled out and swallowed by the black hole. So this gas, actually, as it falls in, goes into orbit, it forms something called an accretion disk. And before it falls into the black hole, it gets very hot. It's falling, there's a huge gravity, a lot of friction, there's a lot of heat being generated, and it radiates. All that heat gets converted to radiation before it falls into the black hole. And you're right, once it's gone in, it won't radiate any longer, right? It may radiate, but we won't see it. It cannot escape. But while it's coming in, it can radiate quite a lot. And for these systems, it gets so hot. It's about 10 million degrees Kelvin. So hot that its primary radiation is in X-rays. And this is why we find them in X-ray observatories through the X radiation. And so that is where the X-rays come from. So when I said earlier that perhaps the systems in the gap we are unable to see, it could be that when black holes come into this region of the gap, for whatever reason, they never have a companion star. Or even if they have a companion star, the star is never close enough. So maybe you don't form an accretion disk.
Yeah.
So if you don't have an accretion disk, we're not going to see it. So they could be there, they could be dark, and we would never find them through our X-ray telescopes.
Interesting. So let's talk about this accretion process a bit more. When we think about dropping an object from a height, it has gravitational potential energy when you hold it up high. And when you let go of it, it loses that gravitational potential energy. It smacks onto the table and it makes a sound. Maybe it warms up the table a little bit. It's sped up. And so you're converting gravitational potential energy into kinetic, into eventually thermal. And I guess something similar is happening here. But I guess maybe what might be confusing is when you think about space. Think about a particle in orbit of the Earth, a satellite in orbit of the Earth. It seems like it's almost stable forever, that there's no... space is empty, and so you would imagine that particle would just go round and round indefinitely. When these particles of matter are in orbit of these black holes, there must be some dissipative process that is slowing them down, a drag force of some kind to get them to fall in, to spiral in. Is it just, you mentioned the word friction there, is it friction in the sense that we would normally think of it, or is there some more interesting physics going on as a dissipative mechanism?
Answer is yes and no. It is really a lot like friction, except the correct term here is viscosity. So friction is when you have two solid objects, one moving with respect to the other. And we are familiar with that. Viscosity is the same thing for a fluid or a liquid. And there, the way it works is, if I take a parcel of fluid and make one part move relative to the other part, say faster or slower, then this change of velocity causes something like friction to operate, and it kind of always leads to some kind of a force that tries to equalize the velocities. That is this dissipation you're talking about, and that leads to heat. Very viscous fluids will be, honey is a very viscous fluid, that it doesn't want to kind of flow past itself. It's kind of has a, coherence about it. Okay, so the idea with accretion disks is the following. Like you said, Earth can go around the sun for billions of years and nothing happens to it. So Earth by itself is not an accretion system. It's an orbiting system. If I put a blob of fluid, not a blob, a big chunk of fluid around the sun, then what will happen is it won't go round and round forever. The parts of the fluid that are closer to the sun will go around faster. The parts of the fluid which are further away from the sun will go around slower. You set up what is called differential rotation. Inside goes fast, outside goes slow. And the whole fluid is in contact with itself. It has got this change of velocity with distance or radius. That will set up a viscosity. It will create viscous forces like friction. It will create heat, but it will also cause the fluid to move down towards the sun because it's kind of losing its velocity, falls in, keeps falling in. We think this is what happens with an accretion disk. Except, I'm just talking generally about viscosity. You can ask, why should the fluid in an accretion disk around a black hole have any viscosity? Can we calculate that viscosity? What is its origin? It's nothing like the viscosity we are familiar with on Earth. It's not like honey. You can put a blob of honey. It will not produce enough viscosity to be an accretion disk. It turns out that it is magnetic fields. So this fluid has got magnetic fields impregnated in it. This is, everywhere in the universe, this is the case. So this gas has got magnetic fields, and then you can show through theory that that magnetic field will grow and will develop in such a way that it will cause an effective viscosity. It will produce heat. It will produce, in the case of our systems, X-rays. So all of this follows from the fact that you've got a magnetized fluid.
So this is just to clarify, this is not the magnetic field of the black hole, which presumably doesn't have any magnetic field, but rather because this material has got so hot, it's probably got ionized, I would guess, and therefore those moving ions, by Maxwell's theory, you would expect there to be magnetic fields generated by the movement of the ions themselves. So it's the disk itself which is responsible for the magnetic field. Is that right?
Yes. So you're right. Black hole itself doesn't have a magnetic field of its own. But the accreting fluid has got magnetic field inside itself. And this is, it's actually, in most cases, probably it's the magnetic field that it already had before it fell on the black hole. Like, the sun has got a magnetic field. We even make measurements of it. It's got a few Gauss, and in some regions, even as much as 100 Gauss, 1000 Gauss. So you can imagine pulling that material out and accreting on a black hole. It comes already with its own magnetic field, which can then be built up, amplified by all the processes you're talking about. And all this works because, like you mentioned, the gas is ionized. So, the atoms are not neutral. The electrons have all been stripped out. So it's what's called a plasma. It's got positively charged nuclei of atoms, negatively charged electrons, all running around in the same place. All of them are kind of spiraling around the magnetic field. It's a very interesting, complex system. But the magnetic field is part and parcel of it, and it participates in the dynamics and provides viscosity.
So the magnetic fields then is a good jumping point for my next question I wanted to ask you, which is about when you imagine flying in a spaceship to see these accreting black holes, you would imagine seeing the disk, and there's all these beautiful portraits and pictures people have created of these things. This disk of material, this cloud of material that's falling in to the black hole, like a 2D system. But besides from that, like a pizza almost, there's something else, and that's the jets, which come out from the poles almost of this, orthogonal to that disk. And we haven't talked about the jets, but it seems like a good jumping off point from the magnetic fields. They are still one of those, I think we can all get our head around the disk. It kind of makes sense when you talk about it, where the disk would come from. But the jets just seems like, who ordered that? Like how do we explain the jets, and why are they so powerful? They're enormously powerful.
Yes. Many systems with disks have these jets. So if you think of the disk as a plate, a somewhat thin, flat system orbiting around a center, these jets are objects that are perpendicular to the plane of the disk. There are two of them. So think of them as, the North Pole sends out one jet, the South Pole sends out another jet. Not every black hole, okay? That's the weird thing. But many black holes with accretion disks have these jets.
What do you mean by many? Like the majority or minority? What we're looking at?
The canonical answer is 10% have jets. This is the old answer. Now people, when they look deeper and deeper, it looks like even the guys that apparently didn't have jets have something. It's much
Smaller
fainter.
jets, yeah.
So it's a question of when do you define that it's a respectable jet, and when is it not a respectable jet? So the respectable jets, 10% of black holes among the quasars. Okay, that's where the best statistics are. Let's not get into the muddy details. So anyway, this thing happens. And these are very, very powerful. Sometimes they can produce more power in the form of just the mechanical energy compared to all the radiation that the accretion produces. Right? That's a huge amount. And they're moving outwards. So the accretion disk is material falling in towards the black hole, disappearing into the black hole. But the jets are coming out. And some cases, these jets can go, thousands of light years, even a million light years away from the black hole, carrying their power in narrow, they're jets, okay? That's what they're called.
Not something you want to fly through, right?
That would
pretty
be an
dangerous.
interesting thing. Maybe far out, not near the black hole, but
Right.
far out. Maybe I wouldn't mind sampling it to see what it looks like. Yeah. So where did that come from? So, I think we have a pretty good story now. The story is, it is magnetic fields. And I understand why you jumped to this topic from the previous topic. So it turns out that if you have a black hole and you got this accretion disk flowing in with magnetic fields, if you can arrange to have the magnetic field pile up around the black hole in a certain ordered and regular way, and I can't, without a blackboard, I can't show you what I mean, but just think of it, a pile of magnetic fields piled up near the black hole with field lines sticking out. If you can arrange that and put a strong enough magnetic field, and if your black hole is spinning, so it's rotating, it's not a non-rotating black hole, if you have both of these present, then it turns out that this is a natural way to send energy out along the axis in both directions, north and south. And it's an idea that's been around for many years, but more recently, because of computer simulations, what we are finding is, if you give these conditions, the jet forms absolutely naturally. You don't need to do anything. The system automatically makes a jet. So many of us, and I'm part of this group, believes that we now know how jets are made. They are made with two ingredients: strong magnetic field near the black hole and rotation of the black hole. You give those two ingredients, the magnetic field automatically carries energy away from the black hole and the accretion disk, carries it away in the perpendicular direction. And we have found that if the spin is large enough and the field is strong enough, that power in the jet can be much larger than the entire power of the accretion system.
It's amazing. And I guess what's so amazing about the jets, there's no classical, you can't explain it classically. You have to have the rotating black hole, which means space-time itself is being dragged around with this lens thirring effect, this frame dragging effect. And so the jets are, if anyone was skeptical about whether GR, general relativity, makes sense or not, the jets are just kind of manifest evidence of it, right? You can only explain them with GR. Is that right? That there's no classical version of this?
That is a very interesting and deep question. I would go back first and say there is a classical version of this. If I had a spinning neutron star, okay, a neutron star is not a black hole. If I had a spinning neutron star with magnetic field sticking out of it, and this is natural, we know that neutron stars have magnetic fields sticking out.
Mm-hmm.
And if you arrange things right and put an accretion disk around the neutron star, you will have all the ingredients you need for a jet. You have a spinning, strong magnetic field, you've got gas coming in an accretion disk, and I would say, barring some details, this guy should produce a jet. How powerful, that's a matter of detail. But I think the ingredients are there. A spinning, magnetized, compact object with some accretion happening around it will, I believe, produce jets. And so, this is the classical analog. It won't be exactly the same as the black hole. And we do see some jets in neutron stars. People see jets in so-called protostars, things that are going to become stars. So that's a different topic. Let's not go into that. So, you can get a jet. To me, the interesting thing is when you say it's a black hole, and you say a black hole really cannot have its own magnetic field, how does it do it? How does it produce a jet? And there, I think all of these effects you mentioned come in. The frame dragging, which is one of the great effects predicted by general relativity. Namely, if you have a rotating object, example, a rotating black hole, space itself is pulled around. So it's as if the entire space-time is rotating, and you put magnetic field lines, they will rotate because they are part of the space-time, and that's how the jet is being produced. So if you accept that some object is a black hole, and you see a jet, you can say, yeah, I have seen frame dragging. That's the only way I know how to make the jet. Turning it around and saying, I've seen a jet, therefore I believe general relativity, therefore it must be a black hole, I think that's a little step too strong. You can get jets without black holes.
So these jets are so powerful, they're moving very, very close to the speed of light, huge Lorentz factors, as we'd say. There's an enormous amount of power. And so if this is ultimately being fueled by the spin and the magnetic fields, but the spin of the black hole is a crucial ingredient, does that imply that the power, if this, by conservation of energy, if something's losing energy, if something's gaining energy, which is the jet, something must be losing energy, which is the black hole. And so do we expect, therefore, the spins of the black holes to be slowing down? And just to add one more ingredient to that question, what is the accretion itself doing to the spin of the black hole as it's falling in?
Yeah, great question. It's in fact something that we have been focusing on quite a bit recently. So let's start with a system, a black hole that's accreting. And let's say it doesn't have a powerful jet. Okay, now the accretion disk itself is orbiting the black hole. Right? I already talked earlier about fluid closer to the black hole orbits faster, far away orbits slower. So in fact, the bit of the fluid that's right next to the black hole, which is falling in, is orbiting quite fast at some fraction of the speed of light, quite a lot of velocity. And then when it falls in, it will spin up the black hole because it's adding angular momentum to the black hole. And so if you just continue with this accretion, the black hole will get faster and faster and faster. And it will reach close to what is called the limiting spin. So there's a maximum allowed by theory. This accretion, if it goes long enough, will push it almost to that limit. Okay. Now let's consider the second system. You got accretion, and it's also making a jet. And you have arranged it so that there is strong enough field, and you get a really powerful jet. Let's say you saturate it, the maximum that you can do with a jet. Typically, these systems actually spin down the black hole. What's going on is, as you also mentioned, you may be still trying to spin up the black hole through the accretion disk. But meanwhile, there's all this power that's coming out in the jet. That has to come from somewhere. In fact, it comes from the black hole. It is removing rotation energy from the black hole, stealing it, so to say, and using it to power the jet. So this is actually a very interesting concept that, everybody says, oh, black hole, terrible thing, it just eats, and, nothing ever escapes. Here is an example where at least the jets are stealing from the black hole. They're actually getting some energy back from the black hole and using it to power these powerful things, which have a lot of consequences in astronomy. So there is at least part of the energy inside a black hole that can be removed, that is available. And this is a great insight that, again, Roger Penrose, I mentioned earlier, he got in the 1960s. He said, spinning black holes, not all the energy is lost. Some of it can be got back. This is, we call it the Penrose process.
Yeah.
And so in fact, that is what is happening with these jets.
Wow. So it's almost like a pressure valve. The accretion disk is trying to spin it up more and more and more. And the more it spins up, the more likely you are to get to the state of a jet. And the jet decreases that spin pressure. It's relieving things back down again.
That's
in equilibrium. That's
and
fascinating.
so you might almost think there should be an equilibrium. The interesting thing is, if you can pile up enough magnetic field around the black hole, then you can keep on accreting. You'll hardly ever spin up the black hole. Even a little bit you spin it up, it's taking away the energy through the jet. And the equilibrium will not be anywhere near this maximum I told you. It's probably less than 10% of that. Almost not spinning. So this tug of war between what the disk's trying to do to the black hole or what the jet is doing to the black hole, that's an interesting thing. It's hardly been studied. I think it's now, thanks to simulations, we're able to do this more carefully now. And we'll probably have some breakthroughs in the next several years.
Fascinating. Now, we're kind of imagining the black hole from this artist's, flying by in a spaceship and actually being able to see everything. And of course, in astronomy, we don't get to see everything. We're very far away. You said the nearest one is hundreds of light years, and of course, many of the black holes are much further than that. So when we look, there's been this enormous achievement that you were a significant role in, EHT, the Event Horizon Telescope, that wowed the world with these first images of what black holes really look like. And they don't look like this naive conception of the accretion disk and the jets, not because that image is wrong, but just because of the way those images were taken. So maybe we could just focus on that for a moment. Even before EHT took its image, what were you and other theorists and expecting to see? What and why did you expect to see what you saw?
That's a big question. Okay. So, right. So the Event Horizon Telescope got these observations. And as you know, they have got images now for two objects. One is the black hole at the center of our galaxy, which has a mass of 4 million solar masses. And the other black hole is the one in the galaxy M87, which is, it's a nearby galaxy, but quite far away. But it's got a big black hole. It's 6 billion solar masses, a lot bigger than our black hole. So as a result, even though the second guy is much further away, it's as easy to observe with our telescope as the one in our own galaxy. They both have...
These are supermassive black holes, right? These are a little bit different from...
supermassive black holes. Thank you. These are different from the ones we were talking about earlier. So earlier we talked about what are called stellar mass black holes, 10 solar masses, lots and lots of them. Now supermassive black holes. There's one in each galaxy, right in the middle, and it's very massive. Ours is a somewhat wimpy guy, but even that is 4 million solar masses.
Staggering. Yeah.
Yeah. Now, it turns out that by the time you go to a 4 million or a 6 billion solar mass black hole, even this so-called event horizon, small though it is, can be observed or resolved using our telescopes. We could never resolve it for one of the little guys. They're just too small, but these bigger black holes are accessible to direct observations. So this was the insight that people had.
So how big are them? Can you give us a sense of scale? Like is it the size of a solar system, the size of Jupiter? Like what are we talking here?
Okay, what we're talking about is for our galaxy, the black hole, 4 million solar masses, its radius is several times the radius of the sun.
Okay.
Okay? The big guy is as big as the solar system. I think it's further out than the orbit of Pluto.
That's
okay?
M87.
M87.
Yeah.
The M87 is an enormous guy, very, very large. Okay? Our guy is still, maybe 10 times the radius of
It's
the
kind of like a gargantuan from Interstellar, a little bit, these enormous black holes.
Enormous black holes,
Okay.
Absolutely, right. So it turns out that in radio waves, specifically millimeter wavelength radiation, if you had a telescope as big as the Earth, you can actually make an image of either of these two black holes, the one in our galaxy or the one in M87. Now, this looks like a tall order. How do you get a telescope as big as the Earth? This is where the Event Horizon Telescope comes. It uses something called interferometry. And it's a technique where you don't need a single telescope as big as the Earth. Instead, you use half a dozen or dozen telescopes all over the Earth and combine them in a very clever way. So even though each telescope is small, since they are separated by large distances, you get effectively a single big telescope. Running this single big telescope at millimeter wavelength radiation is a gigantic technical challenge. And the radio astronomers, they rose to the challenge and they made it work. And about 5 years ago, the first image was released. So this was an image of M87, the gargantuan guy, 6 billion solar masses, measured in millimeter waves. And that was the famous picture that was released in 2019, finally. And then our galactic center was also observed at the same time. And that had its picture was released last year, 2022. So both of them have the shape of like a donut. So there's a ring of radiation and there's a dark region in the middle. And you might say, in a sense, this is what we expected. And this was predicted about 20 years earlier in a paper by Falke et al. And they said, these kinds of objects, our galactic center in particular, if we could resolve them, and if you allow for the fact that radiation doesn't go in a straight line, but gets deflected by gravity near a black hole, you will get something like these rings. And the effect is very interesting. You can have, a blob of gas radiating. And normally in our neighborhood, if it radiates, the rays will go in a straight line. Straight line from the object to you, your eyes. You put the same object close to a black hole, because of the huge gravity, some of the radiation just falls into the black hole and disappears. The part that doesn't disappear goes round the black hole. It gets deflected, goes partly into orbit around the black hole, bends, and then reaches you. So when we are looking at these images with the dark center, basically the dark center represents the region where the black hole is not allowing radiation to reach us. It is sending the radiation off to the side, and then it reaches us, and that's why you get a ring of radiation. So that's the beautiful effect that was confirmed. There is a clear prediction from theory how big the ring should be, how it is related to the mass of the black hole. It all works beautifully. It's a wonderful confirmation, first confirmation actually, that general relativity theory works very close to black holes as well. This had not been known before, though, we had suspected that it should, because if it can form black holes, it should also describe how rays of light travel near a black hole. Now we have experimental confirmation.
So the size of the shadow,
Yes.
so it's this black disk,
Yeah.
surrounded by this bright luminous ring, the photon ring you might call it, of light being bent round. It has a certain diameter, and that's not the diameter of the event horizon itself. It's larger. Why is it not the same as the event horizon?
Yeah, that's a very interesting point, and a lot of people get confused about this. So there is this event horizon. If something is radiating near the event horizon, pretty much nothing will escape. All of the radiation will fall into the black hole. You're not going to see anything.
Mm-hmm.
Then if you go to some larger radius, there is a particular radius called the photon shell radius or photon orbit radius, which is about 50% larger than the horizon. At that radius, if you have a ray of light, let's say you shoot it sideways, perpendicular to the radius, that photon will go round and round the black hole. It'll go into orbit, just like the Earth goes around the sun. Here, a photon will go around the black hole. But this is not at the horizon. This is at 50% larger radius. That is where the photon will go round and round. Now, even that photon is difficult for it to reach us. It can. But all the photons outside of that radius have better and better chance of reaching us, external observer. But each of them goes on a curved trajectory. It doesn't go in a straight line. Curved trajectory. The net result is when you, the observer, finally looks at that picture, the image, the apparent radius that you observe for that ring is not the horizon. It is not 50% larger. It is roughly 2.5 times the radius of the horizon. Okay, I'll give you more precise numbers, but let's say 2.5 times the radius of the horizon. So that's what we observe. So we observe a shadow or a hole in the image, which is about 2.5 times the size of the black hole. So really, when we are observing this ring, what we are measuring and confirming is the bending of light. We are not directly seeing the horizon. No, we are not. But we are seeing the gravitational effect of the black hole, which is so immense that it pushes light into these curved trajectories.
So maybe instead of the Event Horizon Telescope, we should think of it as the Photon Ring Telescope to some degree.
It is the photon ring telescope or a photon orbit telescope. Yeah, photon shell telescope. They are not as catchy as the Event Horizon Telescope.
I get that. But let me just follow on one little thing on this. If you were a particle, a hot lump of material that's falling into the black hole, and you're on the line of sight between the black hole and the telescope, and you're just about to cross the event horizon, that material, even though it's within the photon ring, it's outside the event horizon just about. It would have, yes, there's rays coming sideways from it that would never reach us, or would circulate around forever and ever. But surely there'd be some rays that would emit towards us like a flashlight.
Yeah.
And I'm guessing the reason we don't see those is just because they're completely outshone by all the other luminous material that accelerates around but circulates around the photon ring. Is that right?
It is. Yeah, it's hardly part of the story. Yeah. So yeah, let's take this experiment you have in mind. There is a blob of gas falling into the black hole radially, okay? And it's almost at the horizon. So let's go and sit in the frame of this blob and imagine that the blob is radiating in all directions. You can ask, will this radiation escape or not? Most of it will not. Most of it will fall into the black hole. Only a small fraction pointed exactly in the backward direction will be able to escape. And the fraction that can escape is smaller and smaller the closer you get to the horizon. So that already kills the amount of radiation you can observe. It's really a tiny fraction. In addition, because the material is moving away from you, right? Let's say you're watching the black hole and the material is falling in radially, it's moving away from you. There is something that is the Doppler effect. So what little radiation escapes is actually very, very dim because the radiator is moving away from you. And then there is also a gravitational redshift. So a whole lot of things conspire to kill off that radiation as far as the observer is concerned. So that is why you got the dark shadow. And you're absolutely right. It's not black, black, black. There is some radiation there, but it's very small compared to what you see in the ring. And with the sensitivity that we have, it looks like it is zero luminosity.
Right. And so this I've taken up so much of your time, but maybe a good point to finish on with EHT is the future. And maybe you might wonder, could we one day detect that light that really is up against the event horizon? Or could we detect more examples besides from just these two supermassive black holes? What is the future of not just EHT, but its successors? What are you hoping to see happen in the next decades in this field?
Yeah. We would like to have more objects than just the two of them. It looks like these are the only two that you can observe from the Earth. Given a telescope as big as the Earth, there aren't too many supermassive black holes that are close enough to us to resolve and make pictures. There may be one or two more, which I haven't found, but it's going to be a small number. Mm-hmm. So we would like to have more angular resolution, which means either going to even shorter wavelengths than 1 millimeter, which is awfully difficult sitting on Earth, or going to space. If we could put telescopes in space, then we can get even larger effective telescopes, right?
So like a solar system sized telescope.
Solar
almost.
system, but even something in orbit or something closer to the moon, that would already buy us a lot. Right. So we will start seeing more of these objects and we'll be able to study more of them. Even from Earth, I think we can do better with more telescopes on Earth. Basically, we used 6 or 8. I think it's now up to about 10 or 12. 25, 30 independent telescopes on Earth will really buy us a lot. This is something that people are working on. It's what's called the next generation Event Horizon Telescope, NGEHT. So that will allow us to see more detail in this ring that we have observed, actually see the so-called photon ring, which is an infinitely sharp feature. That would be wonderful to see, because from that we can get some really interesting physics. But then going out into space is, I think, the long-term goal. Then we can really do physics.
Well, that's an exciting future. I hope we can have a whole catalogue of black holes to look at one day in the future decades. Thank you so much for your time. I've learned a huge amount about black holes, and I hope the audience has too. And good luck with all of the rest of your work in this fascinating field.
Thank you, David.
Yeah, my pleasure. So that was my conversation with Ramesh Narayan, celebrated Harvard astrophysicist who has pushed the boundaries of what is possible in modeling some of the most exotic objects in the universe. And I think for me, that was what was really inspiring about this conversation. When I look out in space, as an exoplanet hunter, I tend to think of the universe as a largely empty vacuum punctuated by the occasional star and planetary system. And all of that is fairly easy to imagine because we have it all in our own backyard, in our own solar system. Sure, the worlds will be different and diverse, but it's not too hard perhaps to stretch our imagination to think of what those worlds might be like. But Ramesh is trying to do something completely different. He's trying to imagine and model the detailed physics of objects which there is zero analogy in our solar system, objects which defy any expectation, any anticipation of them until basically general relativity points out these things should exist, these bizarre black hole objects. I think it is an incredible testament to human ingenuity, the human intellect, that we were able to not only successfully imagine them, but get so close that these simulated images that Ramesh worked on were almost indistinguishable from the actual photo that we took using the Event Horizon Telescope, the first ever photo of a supermassive black hole, Messier 87. That's incredible that we were able to do that just from the power of the mind. That is an incredible achievement. And it gives me a lot of courage, a lot of confidence that we can achieve so many other challenges that are currently plaguing our society, both societal and also science questions, health questions, medicine questions, that are legal questions that are facing our society. And when you look at the fact that we are able to achieve something like modeling a supermassive black hole to that incredible level of sophistication, detail, and accuracy, who says that we can't achieve all of the other things as well? I personally take a huge amount of confidence from that, and I hope you do too. And hopefully it encourages you that whatever questions and problems you think are insurmountable, people like Ramesh prove you can do it. And you can, in your mind and with a bit of math and hard work, you can work through those problems and you can tackle them too. So I enjoyed that conversation. I hope you did. If you like these conversations, if you're enjoying this podcast, then please do consider supporting us. The best way to do that is actually just to head to coolworldslab.com/support. That's coolworldslab.com/support, where you can pledge to become a regular donor anywhere from $5 a month upwards, and you can basically support my research team. All of this money goes to research directly, and by helping me out with the research, it gives me more time, in fact, to stop writing grant proposals, and I can make more videos for you, both on the main YouTube channel and, of course, on here on the podcast. So it's all circular, and you kind of have the benefit of knowing that your money is going directly, every penny, to research. I think that's kind of an incredible thing that we are trying to do, and I hope you think that's an interesting opportunity as well. So please do check that out. And as always, thank you so much for watching. And until next time, stay thoughtful and stay curious.